Good day, everyone. Welcome to my YouTube channel, Usano-Goldie RL Marquez. This is differential equations. In this video, I will be discussing a linear differential equation of order 1. A linear differential equation of order 1 is one of the types of first order, first degree ordinary differential equations. When is a differential equation said to be a linear differential equation of order 1? A differential equation is said to be a linear differential equation of order 1 if it can be written in the form derivative of y with respect to x plus y p of x equals q of x. This differential equation is said to be linear d in y. The general solution of this differential equation written in this standard form is given by y times I of x equals integral of q of x times I of x dx plus c, where I of x is equal to e to the integral of p of x dx, or equivalently exp of integral of p of x dx. This function I of x is called an integrating factor to this differential equation. An integrating factor to this differential equation is actually not unique. Any constant multiple of I of x can be considered an integrating factor to this LDE in y. It is also possible that a differential equation is linear in other variable. The derivative of w with respect to t plus w p of t equals q of t is the standard form of a differential equation linear in w with respect to t. And the general solution of this differential equation is given by w times I of t is equal to the integral of q of t times I of t dt plus c. The following are the steps in solving linear DE of order 1. First, reduce the given linear DE in its standard form. The standard form of LDE in W is given by derivative of W with respect to t plus W P of t equals Q of t. The second step is to identify P of t and Q of t in this standard form. The third step, determine its integrating factor given by I of t, which is equal to e to the integral of p of t dt. The last step, solve the general solution given by w times I of t is equal to the integral of q of t times I of t dt plus c. Take note that in this form, p of t is the coefficient of the positive w, and q of t is the right-hand function or expression. Let us have the following examples. Example 1. Solve the differential equation derivative of y with respect to x plus 2 over y 2y over x equals 6x cubed. So again, derivative of y with respect to x plus 2y over x equals 6x cubed. This is LDE if we can express it in the form derivative of y with respect to x plus y p of x equals q of x. This can be expressed in the form derivative of y with respect to x plus y times 2 over x, which is a function of x, and the right-hand side, which is 6x cubed, is the q of x. So this means that this is a linear DE of order 1, and this differential equation is the standard form of this DE. P of x is the coefficient of the positive y, that is 2 over x, and q of x is the right-hand expression, which is 6x cubed. The integrating factor to this differential equation is given by exp of the integral of 2 dx over x. This integral can be evaluated using the integral of du over u. This is the u, which is x, and the differential of x is dx. Hence, the integral of dx over x is equal to ln of the absolute value of x. So times 2, so we have 2 ln of the absolute value of x. So the integrating factor is given by e to the 2 ln of the absolute value of x. So this can be written as ln of x squared from one of the properties of logarithms. So hence, the integrating factor when simplified is given by simply x squared. So again, from one of the properties of logarithms, e to the ln of x squared is simply x squared. The general solution, therefore, is given by y times the integrating factor, which is x squared, as what we got, and q of x is equal to 6x cubed, I of x is equal to x squared. So we have y times x squared equals integral of 6x cubed times x squared dx plus c. Simplifying this, we get 6 times the integral of x to the 5th dx plus c. This can be evaluated using simple power formula where n is 5. So the integral of x to the 5th dx is given by, or is equal to, x to the 6 over 6 times 6 plus c. So simplifying this, we get x to the 6. So hence, the general solution is given by x squared plus y, x squared times y equals x to the 6 plus c. Or, in explicit form, that is y as a function of x, we have y is equal to x to the 6 plus c all over x squared. Example number 2. Solve the differential equation x squared plus 1 times y prime minus 2xy equals x times x squared plus 1 quantity to the 4th. This is linear DE. We can express this in the form derivative of y with respect to x plus y p of x equals q of x. So to reduce this to the standard form of LDE, so first we divide this left and right side by x squared plus 1 because we want our first derivative to have the coefficient 1. So dividing by x squared plus 1 each side, we get derivative of y with respect to x. Negative 2xy when divided by x squared plus 1, we get negative 2x times y all over or over x squared plus 1. And then the right side, when divided by x squared plus 1, we get x times x squared plus 1 quantity cubed because these are similar terms. So when divided by x squared plus 1, this expression, so x squared plus 1 is cancelled, giving x squared plus 1 quantity cubed. So this is the standard form of this differential equation. Again, the standard form is dy over dx plus y. This is negative 2x over x squared plus 1 equals x times the quantity x squared plus 1 quantity cubed. In this standard form, we identify that q of x is equal to negative 2x over x squared plus 1, the coefficient of positive y, while q of x is equal to x times the quantity x squared plus 1 raised to the 3rd power. The integrating factor to this differential equation is given by exp of the integral of negative 2x over x squared plus 1 quantity dx. We can move negative out of the integral sign, giving integral of 2x dx over x squared plus 1. We can evaluate this using the integral of du over u. Let's try. The denominator is supposed to be the u if we want to have it by integral of du over u. Let's check if the numerator is the differential of this denominator. The differential of x squared plus 1 is 2x dx. So this is the differential of u, where u is x squared plus 1. Hence, this integral takes the form of integral of du over u. Hence, the integral is given by ln of u, which is ln of x squared plus 1. Absolute value is not needed anymore because x squared plus 1 is always positive for every value or for any value of x, times negative. So we have negative ln x squared plus 1. So the integrating factor is given by e to the negative of ln of x squared plus 1. Simplifying this, we have e to the ln of x squared plus 1 quantity to the negative 1. So the coefficient of ln becomes the exponent of its expression inside. From property of logarithm, from one of the properties, this is equal to just this expression, x squared plus 1 quantity to the negative 1. So the general solution is given by y times the integrating factor is x squared plus 1 quantity to the negative 1 equals the integral of q. Q is x times x squared plus 1 quantity cubed, and then I of x, that is x squared plus 1 quantity to the negative 1, then dx plus c. Let us evaluate this integral. So first, we simplify this integrand, giving x squared plus 1 quantity squared times x dx. So 3 plus negative 1, that is positive 2. Same base, we add exponents. 3 plus negative 1, that is positive 2. So the integral becomes integral of x squared plus 1 quantity squared times x dx. This can be evaluated using the general power formula. This power is the u to the n. The base is x squared plus 1. Let's check if the differential of the base is in this integrand. So we have x squared plus 1. The derivative is 2x. Unfortunately, this is not 2x. But since 2 is a constant, we can fix it. So our u is x squared with n equals 2. The differential of x squared plus 1 is 2x dx. Derivative of x squared is 2x. So hence, this integral can be written with 2 introduced here, then balance outside by 1/2. So this is now u to the n du after correcting the differential of u. So to evaluate this, we have u to the n plus 1. So that is x squared plus 1 quantity cubed over n plus 1. So that is over 3 times 1/2. So times 1/2. So the integral of this is, when simplified, 1 over 6 times x squared plus 1 quantity cubed plus c. So the general solution is given by y times x squared plus 1 quantity to the negative 1 equals 1 over 6 times x squared plus 1 quantity cubed plus c. So let us write the general solution in a better form. Actually, this is already the general solution, but let us rewrite it in a more nice form. There are many possible forms of final answer actually. It depends on a person trying to simplify this. So for my case, I multiply this by 6. So we get 6y times x squared plus 1 quantity to the negative 2. That is equal to x squared plus 1 quantity cubed plus, so times 6. So we have 6c. So this is cancelled. So there is 6 here. Now I want to eliminate this factor on the left side. I'm going to multiply it by its reciprocal. So, but I have to multiply also the right side by whatever I am going to multiply here. So we get this expression. So multiplying also this by x squared plus 1. So we get x squared plus 1 multiplied to this whole expression. So on the left side, we have only 6y. Now 6z is an arbitrary constant. You can simplify that arbitrary constant into c sub 1. So c sub 1, I let it by c sub, 6c, I let it by c sub 1. So this is one of the possible form of answer. Another possible expressing this general solution in explicit form, that is expressing y as a function of x. So I will just multiply this by x squared plus 1. So this is now simply y. And the right side, we have x squared plus 1 multiplied to this whole expression. Another possible form of answer. So we're done. So this is the general solution for this one, for the differential equation okay, so let's have the third example number 3. Solve the differential equation dx over dy minus x cosecant squared y tangent y equals negative 8 over sine y plus 4. So let's see if this is linear. So definitely it is not linear in y because of the presence of this quantity, this one, and also of course, so obviously not linear in x anymore. So in y. So let's see if it is linear in x. So our goal is to be able to express this in the form dx over dy plus x p of y equals q of y this time. So in order to reduce that in such form, so we segregate x, so derivative of x with respect to y plus x, then the remaining quantity therefore is negative of cosecant squared y tangent y. And the right side, no problem with that. So that is already in the proper position or correct position. So negative 8 over sine y plus 4. So this is now already in standard form. Derivative of x with respect to y plus x, p of y equals q of y. So that's the standard form of this differential equation. From this standard form of LDE, we identify p of y as negative cosecant squared y tangent y. And the q of y equals negative 8 over sine y plus 4. So the integrating factor is given by exp of the integral of negative cosecant squared y dy over cotangent y. Because tangent y can be written 1 over cotangent y, its identity. Now, why did I write it in that form? Because cosecant squared is related to cotangent. This integral can be evaluated, I think, by integral of du over u. Let's see. If I take this cotangent y as u, the differential of this is negative cosecant squared y dy. So this is really du. So hence this integral is integral of du over u. The integral of that is ln of u. So we have ln absolute value of cotangent y, ln of absolute value of u. Simplifying, we have e to the ln of absolute value of cotangent u, that is absolute value of cotangent u. This absolute value of cotangent u is either negative cotangent y or positive cotangent y once we remove the absolute value symbol. So it is negative cotangent y if the value of cotangent y is negative. So that negative, this is positive because this is always positive. Or 0, but for this case, cotangent, I think it cannot be 0, cotangent y. And if cotangent y is positive, so we have cotangent y as the absolute value of cotangent y. As I mentioned, an integrating factor to a differential equation is not unique. So it can be positive cotangent, negative cotangent, it doesn't matter. Let's choose I of y to be cotangent y. Although negative cotangent y, you can use it also. So the general solution of the differential equation dx over dy plus x of y equals q of y is given by this, which is x I of y equals integral of q of y times I of y dy. Let's plug in the values of these functions. I of y, that is cotangent y, so times x. On the right side, we have integral of q of y, that is negative 8 sine y plus 4. And then I of y is cotangent y, so dy plus c. Let's evaluate this integral. So we have this integral is written integral of negative 8 cotangent y dy over sine y plus 4. Let's see what we can do with this integral. Sine y is not related to cotangent. Cotangent is related to cosecant. So if we will able to express this denominator in terms of cosecant at least, so we can find way to evaluate this. So let's try multiplying the numerator and denominator by cosecant, because that is the only way for this sine y plus 4 to be in terms of cosecant. So let's do that. Now we multiply both the numerator and denominator by cosecant y, which is equivalent to 1, as long as cosecant y, of course, is not equal to 0. That is allowed because I did not multiply the integral outside. I introduced this function containing y just inside. So simplifying the denominator, we have 1 cosecant y times sine y, that's 1 cosecant y times 4, that is 4 times cosecant y, giving 1 plus 4 cosecant y. And in the numerator, we have 8 times negative cosecant y cotangent y dy. Let's check. If I take this 1 plus 4 cosecant y as my u, the differential of this is negative cosecant y cotangent y times 4. So for this to be du, I have to multiply this by 4, but balance outside by 4. So let's do that. Multiply by 4 because that is the only constant missing for this to be du, and then balance outside by 1 over 4. So this is now the differential of u. So this is du over u, du over u. So the integral of that is ln absolute value of u for the denominator. So 8 over 4 is equal to 2. So hence this integral is equal to 2 ln of 1 plus 4 cosecant 2 y. So absolute value of that, omitting the constant of integration because we have already here plus c. So let's put this value here. So this integral now is equal to 2 ln of absolute value of 1 plus 4 cosecant y. So we're done. So the general solution therefore is given by x. or tangent y, which is equal to 2 ln of the absolute value of 4 cosecant y plus c. So let's have one more. So this is second to the last. Solve the initial value problem. So this is supposed to be initial value problem. Let me correct this one. Initial value problem. Initial value problem. So that is initial value problem. So we have sorry. So the given initial value problem is 4 plus sin e to the x y prime equals e to the x times the quantity 6 secant squared e to the x minus y cosine of e to the x, subject to the condition that when x is ln pi, the value of y is 1/4. Express the final answer in explicit form, that is y as a meaning dependent variable as a function of the independent variable. So this differential equation is possible to be linear d in y. So let's reduce this to the form derivative of y with respect to x plus y, p of x equals q of x. So that's our goal. So in order to do that, so we distribute e to the x to this expression, negative y cosine e to the x, because this is supposed to be transposed on the right side because it contains y. We get y e to the x cosine of e to the x. And then distribute e to the x to this, so getting 6 e to the x secant squared e to the x, which we are going to retain on the right side. This is function of x, which is q of x. So still not yet in the standard form. We want our y prime or derivative of y with respect to x to be alone. So we have to divide this y prime by this quantity. Of course, dividing y prime by this quantity, we have to divide also this term and then the right side. So dividing by such quantity, we get derivative of y with respect to x plus y e to the x cosine e to the x over this expression 4 plus sine e to the x equals on the right side 6 e to the x secant squared e to the x over 4 plus sine e to the x. So this is already in standard form. Y prime plus y p of x equals q of x. We identify p of x as this expression or function. This is the q of x. So solving for the integrating factor, we have exp of the integral of this dx. Now let's try what integration technique or formula applicable to this. Let's try taking 4 plus sine e to the x as our u. If this is u, the derivative of this is 0. This is cosine of e to the x, derivative of e to the x. By chain rule in differentiation, we have e to the x. So sine e to the x, the derivative is cosine e to the x, so derivative. And then we have e to the x. So in differential, we have e to the x cosine e to the x times dx. So this is the differential of the denominator. Since this takes the form of d over u, the integral is ln of this denominator or this u. No need for the absolute value because sine is always between -1 and 1. So, and plus 4, so it means this is never negative. So we have e to the ln of 4 plus sine e to the x. From one of the properties of logarithms, so this is simply 4 plus sine e to the x. So that is the integrating factor. So for the general solution, we have y times I of x equals integral of q of x times integrating factor d of x. By the way, solving initial value problem means finding a particular solution satisfying the given initial condition. So to find such, we have to find first the general solution. Then after that, we have to find the value of c. Yan. Then substitute. That will give us the solution to such initial value problem, or for the particular solution of such DE. So let's simplify this integrand. This is cancelled, giving 6e to the x equals squared e to the x. So times 6 outside. Let's move this out of the integral sign, getting this. So this is read as integral of secant squared e to the x times e to the x dx, meaning secant squared u du. Secant squared u du. From one of the basic integration formulas, trigonometric formulas for integration. So the integral of this is equal to tangent of u. Our u is e to the x. Secant squared u du. Integral is tangent u times 6. So 6 tangent e to the x. Hence, the general solution is given by y times the quantity 4 plus sine e to the x equals 6 tangent e to the x plus c. So to solve for the value of c, we apply the initial condition x equals ln pi. When x equals ln pi, the value of y is 1/4. So from the general solution, so we are going to replace x and y by these values respectively. So let's do that. So y is 1/4, x is ln pi, so this is also ln pi. So simplifying this, we get 1/4 times the quantity 4 plus sine. This is simply pi from one of the properties of logarithms. So equals 6 tangent of, so same here, this is simply pi, so that we have 1/4 times 4 plus sine pi equals 6 tangent pi plus c. But what is sine pi? That is 0. Tangent pi, which is 90 degrees, that is also, 180 degrees, so that is 0 also for the tangent. So we get 1/4 times 4 plus 0 equals 6 times 0 plus c. Hence, c is equal to 4/4, which is equal to 1. Hence, the solution to the initial value problem, or the required particular solution, is given by y equals 4 plus sine e to the x equals 6 tangent e to the x, then plus 1, the value of c. So substituting this to the general solution, giving the particular solution, which is the solution to the initial value problem. And this is the initial condition. Now, what we are asked to find or to express our answer in explicit form. So we write, or we solve y, giving 6 tangent e to the x plus 1 all over 4 plus sine e to the x. So we're done. So this is the solution to the initial value problem, or a particular solution, where c is equal to 1 to this general solution. Let us have the last one. Solve the differential equation L di over dt plus Ri equals E, where L, R, and E are constants, subject to the condition that when t equals 0, I equals 0. Determine the limiting value of I when t approaches infinity. So meaning when t becomes large. This differential equation is actually the differential equation corresponding to the instantaneous rate of change of the electric current with respect to time. This differential equation represents a simple electric circuit involving electric uh, element L and R with with constant voltage E. So let's reduce this to standard form. So the recorded standard form is derivative of I with respect to t, since I is the dependent variable, plus I times E of t. Then the right side is Q of t. So to reduce that in such form, we divide by L because we want our di over dt to be alone or having a coefficient 1. So dividing by L, we get R over L times I, and the right side E over L. So remember, L, R, and E are constant. So this is the standard form of this differential equation. di over dt plus I P of t equals Q of t. P of t and Q of t happens to be both constant functions. And P of t, R over L, Q of t, E over L. So for the integrating factor, we have I of t equals exp of the integral of R over L multiplied to dt. So the integral of this is t times R over L. So giving I of t equals E to the R t over L. Hence, the general solution is given by I times this integrating factor equals integral of Q of E over L times I of t, which is given by this, dt plus c. Let us solve this integral, evaluate this integral. So, given this integral, to evaluate this, I think this is possible by e to the u, integral of e to the u du. Let's take u to be equal to r t over L. Differential of this is r over L dt. So this is e to the u, but unfortunately this is not du. So we need to multiply by r over L for this to be du. So that's now fixed. Multiply by r over L. So this is now e to the u du. But don't forget to balance outside by L over R, the reciprocal of what we multiplied inside. So again, this is now read as e to the u du. So hence we have e to the u plus e to the u plus a certain constant. So e to the u times L over R, because this is cancelled. E over R. So times e to the R t over L. So this integral is equal to this. L is cancelled. So putting this in this integral as its value, we have this integral equal to e over R, e to the RT over L plus c. The left hand side is I, e to the RT over L. So this is the general solution. But we want the particular solution because we're given the initial condition. So to solve for the value of c, apply the initial condition. When t is 0, I equals 0. I times e to the r t over L equals e over r e to the r t over L plus c. So this is the general solution. So replacing t and I by I and 0 respectively, we have 0 times this. So this is 0. So this is e over r times e to the r over L. So r over L is multiplied by 0. So this is e to the 0, but e to the 0 is 1. The left side is 0. So getting 0 is equal to e over r. Hence, the value of c is negative e over r. Hence, the particular solution is given by I e to the RT over L equals E over R e to the RT over L minus E over L. Let's multiply each side because we want to solve I in terms of other letter. So let's multiply its both sides by e to the negative of e r over lt. So getting I on the left side, the first term is cancelled with e to the negative rt over L, then minus e over r times e to the negative rt over L. E over r is common, let's factor that out, getting e over r times 1 minus this exponential function. So hence, our I is equal to E over R times the quantity 1 minus E to the negative RT over L. The particular solution or the solution to the initial value problem. So that's it. So we're done. So the second question asking for the limiting value of I when T becomes large. So to solve for the limiting value of I, when t is large, we have limit of I as t approaches infinity, that is equal to limit as t approaches infinity of I. But what is I? Now, as t becomes large, e to the negative large is going to be 0. So the limit of this is 0. So plus 1. So that is 1 times e over r. So the limit is e over r times 1 minus 0. So but e over r is constant. So the limit of that is simply e over r. So the limiting value of I, therefore, e as t becomes large is e over r. So that's the final answer. So we're done with those 5 examples. So that's all for my discussion. I do hope you really watched and listened carefully. And so therefore, I expect that you understood the lesson well. Now, to check your understanding, here are a few exercises for you to try. So practice exercises. So find the general solution of the given DE. Number 1, y prime plus y cotangent of x equals 2 cosecant x. Number 2, x y prime plus y, this binomial multiplied to 1 plus e to the x quantity squared equals x e to the x. Third one, y derivative of x with respect to y plus x times this binomial 1 minus 2y squared equals 6y squared e to the y squared tangent of y cubed. And for letter B, solve the initial value problem. X squared y prime equals 1 minus 2xy, subject to the condition that when x is 2, y equals negative 5. The last one, y prime plus y equals secant squared e to the x, subject to the condition that when x is ln pi over 4, y is 8 over pi. Thank you for watching. Please don't forget to subscribe to my YouTube channel, Usano-Goldie RL Marquez. Bye-bye.